It's got to be more complicated than this, right? Well, yes. So let's start making it a little bit more complicated. First of all, let's consider these odd cases here. These are like when we were doing my solubility product things where I had two of a particular ion that I had to take into account stoichiometrically. When H2SO4 goes into solution, it doesn't go into solution to make just one proton. It ultimately makes two. And you might think, oh, well, stoichiometrically, let's just account for this the same way we did with solubility product problems. But the answer to that is, unfortunately, that this doesn't happen that way. It happens as a sequential kind of dissociation. And that's something we're going to save for doing an examination of acid-base problems that involve polyprotic systems, multiple proton systems at the very end of acid-base lectures. On the other hand, we can deal with compounds like calcium hydroxide or barium hydroxide or strontium hydroxide right now because these do not, at least in freshman chemistry, dissociate sequentially. They dissociate all at once. This means then that it is not the starting analytical concentration that I'm measuring at equilibrium for calcium hydroxide. Let's consider a case like this. It's twice that amount. If I start off with 0.1 molar calcium hydroxide in solution, and I've got 0 of this and 0 of this to start, and this all goes away, and I'm forming this, I am not forming 0.1 molar of the hydroxide because for every calcium hydroxide that goes into solution, I'm making twice as much of the hydroxide. And so when I get down to equilibrium, I have 0.2 molar hydroxide from the starting 0.1 molar of the calcium hydroxide. So in this special case right here where I'm working with the alkali earths, and I have calcium hydroxide with 2 hydroxide, barium hydroxide with 2 hydroxides, strontium hydroxide with 2 hydroxides. In each of those cases, you have to double the starting analytical concentration. But otherwise, the math is nice and simple.